Welcome to a follow-up session on the camera tutorials. In this video, I'd like to address a few questions that I got in comments and over emails. Specifically, I want to answer the following questions. Does the camera have world coordinates or is it located at the origin? If the camera is in world space, then how do we place it there? Is it the same as transforming all the other vertices? How do we set the camera to point to the positive or the negative z-axis? Let's go over these questions one by one. So does the camera have world coordinates or is it located at the origin? The answer to both of these questions is yes. That may sound a bit self-conflicting, so let's go deeper into this. Imagine that we're working on an open world game, and for simplicity, we will look at our scene from the top down. So maybe there's a ridge or a mountain right here, a castle over there, a couple of monsters near the castle, and another one there. Where is the origin in this coordinate system? Well, it can be anywhere you want it to be. This is simply a map. You need to decide where the origin is located and in what direction the axes of the coordinate system are pointing. So let's assume that the origin is somewhere between that monster over there and the castle, and let's have the positive x-axis go to the right and the positive z-axis go forward. Remember that since we're looking down on the world from the top, we can only see the plane created by the x and z-axis. The y-axis goes into and out of the screen. In that case, the castle may be at around 1 on the x and 1 on the z, and the monster on the other side of the origin, -1 on the x and -1 on the z. Now where's the camera in this setup? The camera is basically our hero who is free to explore this environment. This means that we need a first-person camera that can move and turn around 360 degrees to look at every direction. But if the hero can move, it means that the camera is going to have a dynamic coordinate in this world coordinate system. It may be 0 if the camera happens to be located directly on the origin, but most of the time it won't. In this respect, the camera is exactly like any other object. It has a world space coordinate which we must update based on the movement of the player who is guiding the hero in this imaginary world. Now remember that I also said that the camera is always at the origin. How does that work? We need to remind ourselves the main goal in this business. There is a virtual pyramid that starts from the location of the camera and goes along its target vector. This pyramid is actually chopped off very close to the camera to create a near plane, as well as further away where we have the far plane. We call this pyramid a view frustum, and it defines the extent of the world which the camera can see from this location. This is a highly simplified model of the human vision, but it is very effective for 3D graphics and makes our life easier. Our goal is to project every object within the frustum on the near plane. The near plane is a rectangle which we can map to the actual window on the screen. Theoretically, we can do this projection using the world space coordinates of the objects on the world space coordinates of the near plane. However, this is quite complex and will require updating the projection equations whenever the camera moves or turns. In addition, we will need to update the coordinates of the rectangle on the near plane because that will change too. The bottom line is that no one works this way because, there's a much simpler alternative. Think about it for a second. Wouldn't it be easier to always assume that the camera is located at the origin and the target vector is aligned with the z-axis? If that was the case, the projection equation could be calculated only once and then be applied on every vertex. But how can this work with the fact that the camera is dynamic in both location and direction? This is where the camera space comes into play, and this point often confuses people. You see, we can think about our current world space coordinate system as a primary coordinate system. We can define a secondary coordinate system using the primary system as a frame of reference. In the context of the primary coordinate system, the origin of the world is defined as location 0, 0, 0, and the three axes are 1, 0, 0, 0, 1, 0, and 0, 0, 1. The camera coordinate system, which is a secondary coordinate system here, has its origin at the location of the camera in the world. The camera target vector is its z-axis. The vector that points from the camera to the right is its x-axis, and the vector that points up from the camera is its y-axis. In the following example, the secondary coordinate system is located around 4 on the x and -3 on the z. Let's assume for simplicity that the target vector of the camera in the world is 0, 0, 1. You will see in a second how this helps us. What we can do is switch roles between the primary and secondary coordinate systems. We can actually define the primary system, the world, using the camera system as a frame of reference. After switching roles, the camera is now the primary system, so it is located at the origin, and the origin of the world is now at -4 on the x and 3 on the z, exactly the opposite of the camera location in the world. This is easy to calculate in this case because I assume that the x and z axis of the camera are aligned with their world counterparts. When they're not, it's a bit more tricky to calculate, and you can find all the details in the tutorial on camera rotations. We can now apply the same method to calculate the world space position of all the vertices in the camera system, which has become the primary frame of reference. Notice that not the vertices nor the camera have moved an inch. Everything has two position coordinates in relation to the two frames of reference. The important thing is that when the camera system becomes the primary system, it is guaranteed that the camera is always located at the origin and the target vector is aligned with the z-axis of this system. The only thing that remains is to calculate the position of the vertices using the camera system as a primary frame of reference. This is known as the transformation from world space to view or camera space. Once in camera space, we can apply the projection matrix and do the projection on the near plane. This matrix can be calculated once because we know how things are set up in the camera space. Make sure to watch the videos on perspective projection and camera space to understand how these transformations are calculated. If the camera is in the world, then how do we place it there? Is it the same as transforming all the other vertices? This is where the vertices in the camera diverge somewhat. The vertices are transformed from local to world space by applying a world space matrix on their local position in the vertex shader. This matrix is constructed using the scale, rotation, and translation of the model that contains them. But in the case of the camera, there is no point to talk about a local coordinate system because it is represented by a single point and a target vector. The camera itself is never rendered, so we don't need to project it or anything. We simply need to place the camera directly in the world, that is, to assign world coordinates to it, and move it based on the player's actions. As we discussed earlier, we use the camera world space location and target vector to construct a matrix to transform the world space position of the vertices to camera space using the camera as a frame of reference. How do we set the camera to point to the positive or the negative z-axis? Some people prefer to have their camera point to the positive z-axis. This is called the left-handed coordinate system. Others prefer that the camera point to the negative z-axis. This is the right-handed coordinate system. I plan to do a deep dive into this topic in a future video, so for now I'll just answer the specific question. How do we choose between left or right-handed system? In the perspective projection tutorial, we saw how the projection matrix maps z values between the near and far planes to 0 and 1 respectively. Z values that end up negative after this mapping are considered behind the camera, so they won't be rendered, and greater than 1 are too far to be rendered. The choice between left and right-handed systems is done in the construction of the perspective projection matrix, and specifically the 3 cells that I have marked here. The development of the 2 cells on the third row is a bit complex, and I covered it fully in the perspective projection tutorial, so will not repeat it here. The 1 in the 4th row is there in order to copy the original z into the w component. The rasterizer divides the position vector that comes out of the vertex shader by w, which is actually the original z, during the perspective division step. This makes z values between the positive range of z near to z far map to 0 to 1. In other words, this is a left-handed coordinate system. If you look up the corresponding matrix development for the right-handed coordinate system, you will find explanations like the following, which uses similar values in the third row, but with different signs. In addition, we have -1 in the 4th row. This will flip the sign of z when it is copied into w. This matrix will map the negative range of -z near to -z far to 0 to 1, which will make them visible on the screen. I understand this explanation was a bit high level, however, the full development of the matrix is out of scope for this video. The bottom line is that you need to decide whether you're mapping positive or negative values of z into the range that goes into the depth buffer and develop your projection matrix from there. This will lead you to one of these two options. Okay guys, that's it for today. I hope you found this video helpful. Let me know in the comments below if you have more questions on this topic. Thank you for watching, and I will see you in the next tutorial.